recording.
Hi everyone, welcome back. So we're talking about gravity this week. This is Gravity Week. And just to reiterate what I'm going to talk about, clearly it's like gravity in the universe. We have a full planetarium show for you later. And so I try to point out to you either which crash course astronomy video I would like you to watch, or which book sections. They're also linked to the Blackboard, just to make sure that you know that. I secured a place in the research building on Friday afternoons for office hours. So if you feel not comfortable asking me right after class, you can drop in anytime between 1 and 2 o'clock, really. At 2:30 I have to go get my kid. And so on Fridays I will be available. There was also an announcement to that effect. Yay, I don't have an office, but at least I have a place to do office hours or drop-in hours. I won't be there next Friday, unfortunately, because we're having like a university-wide thing. But other than that, I should be there. So Kepler's 3 laws was how we got to thinking about gravity, right? So this is where the nature of gravity started to really come to humanity's attention, where we realized that planets weren't on perfect orbits. They weren't held together by crystal spheres or anything like that. They seemed to just be hanging in space, following a very set path that followed an elliptical orbit, and had very strict rules about like how their speeds, the speeds related to how close they were to the star. Remember that they sweep out the same area. So if it's far away from the star, you get a slower moving orbit. You're moving slower in orbit, and as you get closer, you move faster because you have to still sweep out the same area. And then the total lap time relates to the size of the orbit, as the period squared is the average distance cubed. And that seems to hold throughout our entire solar system. So we're basing this off our solar system, and please keep in mind, even though you've all sort of lived in the era that we knew about planets outside our solar system, we've thought about planets outside our solar system for a very long time. But we've never actually had good evidence for them. That was only starting in 1995. So that's really like this century kind of science. So we've based a lot of our ideas about planets based on our own solar system. From that came sort of Newton came up with the laws of motion. You have this in, I think also middle school science class, maybe high school science class. And then you end up with, here. So the third law of motion is actually something that is important for actually building planets. But from Kepler's laws, you can infer that this is the force that has to be acting on between the sun and the body in its orbit. That this is the gravitational force acting on them. So the distance and the 2 masses are the real variables in how strong the gravitational pull is. If you are far away from the said body, from the sun, for example, your gravitational pull is less. That's where distance comes in, and depending on if you're close to a massive body or a much smaller body, that also affects how strong the gravitational pull is. And so today we're going to talk about what that implies for if you're not one little point on a diagram, right? Usually if you have this, you sort of get like a little circle here, a little circle there, and it's like, yeah, there's a pull between the 2 of them. They're really far apart. So there you go. And so this is how this is usually illustrated, where you have like mass 1, mass 2, and the 2 of them interact depending on the distance between them. But gravity acts, while it's very not a terribly strong force typically, it acts on great distances. So we see this happen on astronomical scales, not just our solar system, but larger and larger still. And so if we get that gravitational pull, so this is the other way that you can sort of do that as well. So both that object A pulls on object object 1 pulls on object 2, and object 2 pulls on object 1, right? They attract each other. And that attraction is directly proportional to like how much mass, how much stuff they have. And that mass is the same mass that tells you how fast you can actually accelerate something. There's no reason for that to be the same, but it does seem to be the same. Now, tides are sort of what happens if you take a body that isn't a perfect point, or a billiard ball that we just showed, like physics loves the billiard balls, right? They love their spheres, and actually all physicists love like nice simple system. But if we get something like this is a little messier. We now have a large ball of granite, mostly covered in water, and so there's a bit of a difference between, even on the distance between the Earth and the Moon, there is a difference between the gravitational pull on the surface on either side and in the center of the Earth. And so you feel a greater pull if you're closer to the Moon, you feel a lesser pull if you are further away from the Moon. Now that means, or you can basically say it like this: I have a greater distance, I have b plus a here as the distance for the magnetic pull that I'm feeling here, and I have b minus a as the distance if I'm feeling here, and this is the average gravitational pull. So I'm having more pull here and less pull there, which means that you sort of squish the water sort of goes of the Earth sort of have bulge over here and over here. And so the net effect is that if you are then rotating underneath that, you have that bulge happening on the far side and on the close side, on the near side, you get 2 full rotations of tide, cycles of tide in that 24, well, slightly more than 24 hours, because you actually have to catch up to the line of 24 hours and 15 minutes. So this is why the tides shift this is why tide tables are important, because it's not every day at exactly the same time. So you get low tide and you get high tide. Now, we're in landlocked Kentucky with a river that isn't really adhering to this. So who here has actually seen the tide come in or the tide leave? Who's been to the ocean? Fantastic. You've lost your sandcastle to the incoming tide, as we all have. All right, so that's where one set of tides comes from, because the Moon is the nearest, basically, big mass near us, and so you get tidal effects of our Moon on our ocean. But because it's also the other way around, if you have a watery basin here on the Moon, or say that the Moon was a little malleable, it would also have tides, and this becomes important in a minute. But so the Moon-Earth system has builds tides, but also the Sun-Earth system makes tides on our Earth, right? So if you have the Sun-Earth making that difference in gravitational pull, so having like a bulge on either side, you'll get a solar tide, and if you either have new moon or full moon, so basically if the moon's on the far side, fully illuminated by the sun, or the new moon where it's illuminated from the back, and so we don't see the moon, we have lunar tide and solar tide acting together. So you get an extra high tide and you get an extra low tide. And so, but if it's in a first quarter moon or a third quarter moon, the lunar tides, which are the most noticeable one, and the solar tides sort of cancel each other out. So you get not as high tides and not as high low tides. So, funny enough, we have spring tides. Who has heard of the term spring tide? A few of you, especially if you live close to the seaside. Spring tides mean, plus storm means, the levee could break or the levee could overflow. So spring tides is where you get extra high water, extra high oceans. Neap tide is when everything is sort of canceling each other out to a degree, right? The solar tides are not as big as the lunar tides. So the 24-hour period of that comes because the Earth rotates underneath that, lump, so to speak, right? So it rotates underneath. It tries to drag the oceans with it, so you kind of get a slight offset. Here's a GIF of what that looks like. So you've got the Earth rotating, you've got the Moon and the Sun in a line, then you get a spring tide because you've got both the solar tides and the lunar tides coinciding. And if I'm like a half, quarter moon you have two cycles. One of them is the Earth rotates underneath the tides, underneath the water, so you get a high tide, a low tide, a high tide, and a low tide during a day. And then during the month, you have spring tides, really high tides, really low tides, really high tides, really low tides. During those days, those are called spring tides. And then if you have neap tides, you basically in a 24-hour period you don't get as high a high tide and as low tide. So there's two cycles. There's a daily cycle and there is a lunar cycle. With me so far? All right. So you can imagine that this sort of drives a lot of stuff, a lot of cycles of life on Earth, right? If you have a lunar cycle that basically fills the tide ponds that life is trying to, move out from the ocean onto the land, this makes a big difference. And so what is the highest tide? The solar tide, the lunar tide, the neap tide, or the spring tide? What is the highest tide that I can get on it? 41. Yeah, you knew this was happening, right? I'm training you to have this piece of paper ready to roll. 2, 3, you all got it right. Fantastic. All right. What is the lowest tide? A solar tide, a lunar tide, a neap tide, or a spring tide? 41, 2, 3. The lowest tide. The lowest tide. Ooh, I'm going to walk around and you're going to talk to your neighbor, even if the two of you agree, and convince them why you're right. What is the lowest tide of this? You've got about 90 seconds. Voting in 1, voting in 2, and voting in 3. Oh, I see people have changed their minds. Okay, but this is good. Let's go over it one more time as this thing loops around, right? You get the biggest extremes in spring tide. You get both the highest tides and the lowest tides. Low tide is also important if you're trying to, dock a giant ship. And so you get the biggest extremes of solar and lunar tide coincide, and you get the lowest tides as solar and lunar tide. Low tides coincide. So you actually get extra low, you get more extremes. So you get the lowest low tide and the highest high tide. Without the moon, which tide would remain? A solar tide, a lunar tide, a neap tide, or a spring tide? Which one of these would stay? 1, 2, and 3. Yes, the solar one would be there. So even if you have a watery world that doesn't have a moon, because our moon's kind of unusually large as far as we can tell. No other big rocky planet seems to have one. But you still have, nearby sun, so you will still have tons of solar description. You'll notice that in lots of other places. The effects can really be dramatic. This is from this is the illustration from the Weather Service. Basically, if you have you've puttered up, you've docked your boat, you're going for lunch. This is a really long lunch, and so 6 hours later, you're trying to leave port, and you're better off walking. And so one of the most picturesque places to illustrate this with is Mont Saint-Michel in France, which actually is a medieval castle and abbey that they built on a place where everything actually floods about twice a day. So it's, you can get there, you can drive up there half the time, and then you would basically be stuck during high tide, especially during spring tide. And so I have a group work just to get us on the tides part. Now, this is all illustrations from our Earth. But what I'm trying to get across, and what hopefully you'll leave with today, is that that ties tend to not just work, like this is what you've had probably in high school if we talk about high school ties, right? So this is, if you've had ties in high school, then you've heard this. And yes, they are important for Earth, and it's one of the outstanding questions whether or not you need strong ties like this, for example, for aquatic life to move on to land. Like that's a whole discussion that various biologists are having. So is this important for other planets as well? And you'll find out, and this is what I'm trying to say, is that we're going to encounter tides all the time, on all kinds of different scales. That's the whole point. Tides are everywhere. And that's what we're going to illustrate here. Any left over here? I'll try to talk and hand it out. extremes, right? There's extreme high tides and extreme low tides. So we're in spring tide, and you might more chance of the rubber running by, but so there's so high tides that it spills over. Yes, and higher the neap high tides, lower the neap tides are sort of not a big difference. The average is here. It's starting to sound like it was the noise level is going. So the purple is the lunar tide, and the yellow is the solar tide. And so if you get that, if you see where the lunar effect is happening, so here's the lunar effect and then the solar effect. So right here, here we go. So this is the version that isn't moving, right? So here's the version that's not moving, but everything is being labeled. This is why I like doing both, because like I like moving pictures. This works for other people, right? So if you have the moon either side, so the moon, Earth, and the sun are one line, that means both the bigger effect here is the lunar tide and the solar tide sort of reinforce each other. That means on this side and on this side you get higher high tides, but on these sides, we're looking at the top down, right? The moon is sort of looking like this, and the Earth is pointing around the sun like that. Looking at the pole of the North Pole here. And so if you're looking at that, like if you're standing, here, then your low tide is extra low because the water has been moved to either side. So you get a high tide and extra low tide. If the moon is in the first corner, and so this is the neat part, you can actually see from the moon where we're going to be at, right? If it's fully illuminated from the back, so you get a completely dark moon, a new moon, or it's fully illuminated, you see a full round moon, you know, oh, it's springtime, right? I can either not see the moon at all, or it's fully illuminated. If I see a quarter moon, either because it's on the waning or the waxing end, we'll talk about that in 2 weeks' time, but you get that on either side, like if it's half illuminated, you know that the lunar tides are sort of, you're in the middle of the low tide for the solar tide. And so they sort of cancel out. Not perfectly, but you don't get as high a high lunar tide, and you don't get as low lunar quarter. So basically the solar tide is half canceling that out. So, suppose you are now an engineer working on coastal defenses. What do you plan your levee? At what level do you plan your levee for? Do you plan it for the neap tide, high tide, or for the spring tide, high tide? Spring, right? Worst case scenario. You don't want to plan for just, half the time it'll keep the water out. That's not going to make the people on the dry side very happy. So, let's see where I'm at. Okay, so there's one more thing that happens, and so this is a busy slide, I'm sorry. One of the things that happens is that, our Earth is moving underneath that bulge of water. So really what it's trying to do is pull that water with it, right? And so you get that bulge slightly delayed as, the water is reacting to being pulled by the moon. And that means you get a slight offset, which means it pulls the other way than the Earth is rotating. So it's slowing down the Earth. It's also doing the exact same thing for the moon. So two things happen. Our day, because of that friction, slows just slightly. 400 million years ago, we had a 22-hour day. 900 million years ago, so, I'm not a dinosaur fan, but it's like, this is no longer T-Rexes, right? This is weird aquatic creatures, but they had an 18-hour day. So we actually had shorter days in the earlier, here still retained their enthusiasm for dinosaurs, and nobody wants to admit to that they were enthusiastic for it all. Do you remember what 900 million years ago know what that error is called. I don't. Okay, I need to look it up. My point is, dinosaurs had a shorter day, and that gravitational attraction from the moon has slowed our day and actually synchronized also the face of the moon, which side it is facing. It's called tidal locking. So you get a tidal locking of the moon, and you get a slowing down of our day because we are liquid and sort of sloshes over here, and actually pulls it back. So the moon gets a synchronous orbit. It actually starts rotating that its orbit and its rotation line up because of that effect, because this bulb also pulls on the moon to sort of stay in it starts locking that up. So tidal locking, that's the term that I want you to take away from that, is a thing, and we know it's a thing because we see this roughly the same side of the moon all the time, right? Because it rotates at the same speed that it orbits. And this happens also to other bodies, right? So this can happen to exoplanets. And if that happens, so which other solar system objects experience tides? The Earth and the Moon, Moon and Fire, the Earth, the Sun, Earth, and the Moon, or any two bodies in the solar system? Voting in 1, voting in 2, and voting in 3. Yes, this happens everywhere. Okay, so that tidal locking, meaning that if you have something that sloshes, if it's not basically a solid rock, if it is even still hot on the inside, it will actually have that tidal effect, and that means it also, if you have an orbital motion, it will actually start pulling the same side facing the larger body. So moons have a tendency to start tidal locking, but also planets, other planets, if they're near their other suns. So, for example, Mercury is exactly the same thing, where its day and its orbit are locked. The moons of Jupiter are being tidally locked. And very likely planets around other stars have the same thing. So if you keep spinning, that's great. You sort of distribute the heat all around the surface. However, if you're tidally locked, you basically have one side that is completely solid, frozen solid, and the other side, being baking hot. This is not a pleasant place to put life, right? This is a part where it's like, it is temperate right here, and essentially you put one hand out, like this freezes and this bakes. This is a terrible place to put any kind of life. So tidally locked planets are sort of out, and so we're trying to find out which of the exoplanets that we're finding are in fact tidally locked by seeing the temperature changes. So we have that difference in pull, right? We have the average pull here, but here we have slightly less, and here we have slightly more, and that means it bulges out on either side. And so what happens if A becomes larger with respect to the distance, right? I have a fluffier, but the mass stays the same. I'm just making it fluffier. Do I get a bigger effect of the tidal forces on the surface, less tidal forces on the surface, or do they stay the same? Do I get a bigger difference on this other side or not? I got an almost perfect mix. It means that I'm going to do my loop, and you are going to turn around to your neighbor, even if the two of you agree, and explain to you them why your answer is right. You have 90 seconds to do so. Voting in 2. Let's see your your opinions. Voting in 3. Let's see them. It's so funny. You all basically change
Wow, I
sides.
see lots of color back here.
Yeah. All right. I've got B and I've got A. Basically, the room split, which is also fantastic. All right. So what's happening? This is the tricky one. If I add more to A, this becomes a bigger number, which means that this force becomes smaller. Right? If I add greater to A, this total number gets smaller, which means this becomes a larger number. Yeah? This becomes even smaller, this becomes even larger, which means the total pull becomes greater. So if I have a fluffier object, it experiences bigger tidal effects. So if I have a low density object that's coming near a mass, a big mass for example, it will experience more of an effect than if it's small and dense. So if I've got something nice and compact, it will probably survive tidal forces. If I've got something fluffy, sort of, think something fluffy and spongy in space. Well, comets, for example, these things are basically clumps of rocks frozen together with ice. They're not particularly dense and well put together. So if they get closer to the sun, A, they get warmed up, and the B part is they could fragment because of the gravitation. We actually saw that with one of them called Shoemaker-Levy, and that was near Jupiter, and Jupiter basically broke it up into a bunch of fragments. So what happens if mass 2 becomes larger? And I do the same thing, right? What happens if I put a higher number here and here? Voting in 1, 2, 3. Do I get a bigger difference? Again, I've got a perfect split. It looks like a perfect split. What happens to the difference, right? The difference between those two forces become bigger if I make mass 2 bigger. 90 seconds, drink your neighbor, convince them why your answer is right.
Like, do you made M1 bigger, more, but also the thing is already big anyway, so maybe possibly
majority A. Yes, we've got more pull on this side. Oh, you sure? There's also more pull on that side. The whole thing pulls more, right?
Sorry, can you repeat the question?
Okay. Looking for the difference between those two forces, right? And if both of them become bigger, the relative difference becomes bigger. Because I'm increasing the force here and I'm increasing the pull on that side. The difference also becomes bigger because, well, both forces are being pulled at. The whole thing is being pulled at. So if I fly by something massive, or if I'm, fluffy, like I'm a relatively large sized thing with respect to the distance. Like if my distance is really, really big and it's a rounding error. For example, right now, I'm not really feeling the effects of the sun's tidal forces on my body, but if I compress the sun, well, let's move that out. But let's go, say I go near a supermassive black hole, that's the mass of the sun, and I go really, really close, right? Say I go, the black hole is at Drew. So this is 15, 20 meters maybe away, and I am 2 meters, so totally it's a 20%, 10% of the distance. Like that's a big difference. I'm getting a big effect between my head and my feet. Suppose that I'm lying down, right? Like my feet are feeling way more tidal force being pulled apart. Because I'm actually now so close that I'm feeling the difference. So that my size is comparable into the distance. It's a reasonable fraction. The other part is that my mass is absolutely negligible, but the supermassive black hole that Drew has in his pocket is actually, 1 solar mass. So suddenly I get a lot of of force in total, and then also the difference is now noticeable. And so you get something called spaghettification, and that's being pulled into the. So that's what these two leading questions are supposed to do, right? You're supposed to. My point was that depending on how big this is, so how extended that mass is, and how massive the other mass is, and how close you are, if you configure it right, you really feel tidal forces. They're always there, but you can actually see the effect. So the answer is more tidal forces if you increase the force, right? So, okay, so now we get to the fun part, the planetary. Yay. All right. That means we need to figure out how to. Do we know how to put the AV off here?
Yeah.
I'm going to stop the recording because the recording of the planetarium with my iPad is completely pointless. So if you missed it, you missed it.
Are you gonna come back to slides and?
Nope. This is it.